So today I'm going to talk about, signifying nothing, right? Signifying nothing, which is important. That it's about signifying nothing with the discovery of zero, or the invention of zero, however you want to describe that, and its importance, whether it was important, and or whether maybe that there's another story that's important behind this story, which is much more interesting. And that's the story about the history of calculation, of computers, of basically all civilizations in history had ways of doing adding, subtracting, multiplication, and division. Right, they had these ways of doing it with mechanical computers. Right, so what we're going to look at here is we're going to look at the zero that we use in our mathematics, and see how that fits in with that history. Okay, so talking about mechanical computers, does anyone know what this is? Abacus, right. Has anyone used one? Yeah, okay. Oh, there's a few people here. That's great. All right. So there's not too much mathematics you need to know for this talk, but just basic stuff, really. So to count with this, how do we do it? We're just going to count at the moment. So 1, 2, 3. How are we going? We've got 3 beads. We've counted to 3. Let's keep going. 4, 5, 6, 7, 8. Now you've got to watch what happens now. I go to 9, and then I push that across 10. Okay, did we see that? I got to 9. Whoops, wait a minute. I got to 8, 9, and push that across to 10. So these are 1s, and these are 10s. And now I can keep counting. 10, 11, 12, 13. See, the maths isn't so hard, is it? Right. Okay. So don't be scared away. You don't have to walk out of the room with the maths. Okay, so now we can count by tens, right? Because these ones here are tens. Those are units. So we've got, 13, 23, 33, 43, 53, 63, 73, 83. Okay, and then 93. And watch this, 103. Okay, so what we've got here is we've got what they call place value, okay, or where the beads on this line are units, the beads on this line are tens, and the beads on this line are hundreds, and it keeps going down. With the decimal system, with the base 10 system, you go in that way that we're all used to. But look what's happening here. We've got 3 units, and we've got 100, but we've got no tens. Okay? There's nothing on the tens line. So an absence signifies an absence of any value of 10. So we've got a presence of 3, an absence of tens, and we've got a presence of the 100 unit there. Now, how would we write this down? Okay, so we'd write the 3 down. Okay, and we'd write the 100 down, and we've got our 103. Simple. Now, does anyone remember Roman numerals? So with Roman numerals, the 3 is just like 3 marks, right? 3 I's, like 3 B's. And then the C is for 100. Okay, and the C for the Romans stood for centum, which means 100. So it was just the initial of 100. Now, how do we do it in our system? Our system is called the Hindu-Arabic numeral system. And the reason it's called that is because it came from India via the Arabs in the Middle Ages and then came to the West and was eventually taken up in the late Middle Ages. So we'd write down the 3 there and we'd write down the 1 there. So 103. Something's missing, right? Let's do it again. 103, no problem there. 103 in the Roman numerals, and then we've got the Hindu numerals there. So what we can do is we can turn this around on its side, like an abacus, and we can think of it in terms of columns. And a lot of these ancient counting systems, counting tools, used columns rather than beads on a wire. So you've got the ones column, the tens column, the hundreds column, and we've also got that written there in the Roman numerals at the top. So you've got 3 beads or 3 pebbles or whatever it is in the ones, and you've got 1 in the hundreds. And so you can convert that directly, right, to the Roman numerals. Okay, so you just change the beads to the numerals, and then you get the Roman numeral there. So you can say there are 103 sheep, right? But what about with our Hindu-Arabic numerals? I just call them the Hindu numerals there. So we've got 103 sheep. Is that right? We've got 1,003 sheep. We've got 13 sheep. Now notice here, the problem is when you write them out like this, when you say 103, when you say the words or write the words, there's no problem with just not mentioning the tens. Right? When the Roman numerals, because 100 is C and 1s are I's, and as we know, X's are 10s. There's no X, there's no 10s. You just leave it out. But with this system, because it's a place value notational system, you need to mark those columns that are no longer there because you've come off the counting board. So that's where you get the zeros, right? That's what the zeros are for, as placeholders. How are we going? Nothing too complicated? All right. So with place value here, the order matters, okay? And that's why it's so good. People might remember before they got their handheld computer at school, learning how to add, subtract and multiply and so on, it was very important to keep the column. And that's why you needed the 0, and it's very easy to add up. But look at the Roman numerals. They're kind of interesting too. Because what you can do is you can have a few Roman numerals together, right? Adding them up is just like pushing them together. You need to maybe rearrange the Roman numerals to get them in the right order, but order doesn't really matter. And I should note at this point that we're used to, with Roman numerals, having 4 as 5 minus 1, like down here, or 9 as 10 minus 1. They didn't have that in the ancient times. They just had 4 as 4, right? Not this system. So order didn't matter at all. You could just rearrange the numerals and it would be the same. But of course, with our Hindu numerals, if you just ran them together, you would get a completely different number. And so you could do it in a different order with the Roman numerals there, and it would still give you the same number. Whereas, of course, if you did it with our Hindu numerals, you couldn't get it. So in Roman numerals, place order doesn't really matter, but it does with our Hindu numerals. Okay, so what is this 0? What is this signifier of nothing? Well, it's a notation to mark an empty space, an empty column, an empty bar on your abacus or whatever it is. It signifies an absence. So it's, if you like, a notational presence that signifies an absence. It's signifying that there's nothing there, which is kind of a weird thing, isn't it? Now, it also so that's as a placeholder in this type of numeral, in these place value numerals, but it's also a number. Now, what does that mean? Think of, how many sheep do I have? How many sheep do I have? I have 2 sheep, right? I have 1 sheep. How many sheep do I have? I have no sheep, right? How many fish did you catch today? Oh, I caught 10 fish. How many fish did you catch today? I caught none. So, 0 signifies the number 1. Okay? So, this is a bit of a distinction. They really mean the same thing, right? there's nothing in this column, so you put a 0. But here, this is 0 as the number. As not even 1 is the way the Greeks used to term it. Not even 1. 0 signifies none. So that's 0 the number, and this is 0 the placeholder. So that'll be important in our story. Now, 0. How important is 0, the invention of 0? Well, in this book, it says the invention of 0 is one of the greatest achievements of the human mind, a turning point in the history of science and culture. Without 0, there would be no modern mathematics, no physics, no chemistry, no astronomy, and no technology, computer technology, as we know today. This guy says, in the history of culture, the discovery of 0 will always stand out as one of the greatest single achievements of the human race. The discovery of 0. And this book was published just last year, and this actually gave me the impetus to give this talk. William Dalrymple, he's singing up the praises of Indian science in the 2nd, 3rd and 4th centuries, which was marvellous. But he says the concept of 0 is one of the greatest abstractions of the that the human mind has ever achieved. So this book is about 0 as a dangerous idea. So there's a bit of drama in here. The invention of 0 immensely simplifies computation, freeing mathematicians to develop vital mathematical disciplines such as algebra and calculus, and eventually the basis of computing. But it came from India, it went through the Arabs, it was presented to Europe, but the Christian Europeans rejected it for centuries. And the clash over 0 was the battle that shook the foundations of philosophy, science, mathematics, and religion. So here's some more quotes. 0's late arrival was partly a reflection of the negative view of the concept of nothing. Western philosophy is plagued with gross misconceptions about nothingness. That's why it wasn't accepted. The 5th century Greek philosopher, it goes all back to the Greeks, right? The 5th century Greek philosopher Parmenides proclaimed that nothing cannot exist. Nothing cannot exist, since to speak of something is to speak of something that exists. Now, Parmenides did actually say something like that, but he put it another way around. And then it goes into Christianity. After the advent of Christianity, religious leaders in Europe argued that since God is everything that exists, anything that represents nothing must be satanic. In an attempt to save humanity from the devil, they promptly banished 0 from existence, though the merchants kept using it secretly. And here's another one. The Greek universe created by Pythagoras, Aristotle and Ptolemy, the astronomer, we'll get to him, survived long after the collapse of Greek civilization. In that universe, there was no such thing as nothing. No such thing as nothing. There's no 0 because of this, the West could not accept 0 for nearly 2 millennia. For nearly 2 millennia, the West rejected 0. Before they could accept 0, philosophers in the West would have to destroy the Greek universe. So the Greeks gave us our concept of what experience is all about, what our universe is. It was given to the Christians, and it had to be destroyed in order to introduce 0. Now, various versions of this story have been published in various popular science books over the last 50 years or so. Here's one important one, from 1 to 0. We all knew about 1, but then we got the invention of 0. And we've got 0, the dangerous idea. We had that other book about numbers that we mentioned, Signifying Nothing, the Book of Nothing, that the nothing that is, the nothing that is, a natural history of 0, a history of 0, nothing matters, a book about nothing, and we have, you need it for computing, it's zeros and ones, isn't it? And then there's a kid's book, a nice kid's book with a bit of drama in there, the number that almost wasn't, because we resisted it. And then recently, this Finding Zero, where this chap goes to actually Cambodia, where the first Indian zero, well, the first surviving Indian zero, is actually on a temple in Cambodia and also on other temples in India. And then we've got William Dalrymple's book as well. So these guys are all telling variations of this story. And I'll give some of the points that they make. The first is that zero is elementary to modern mathematical science. Okay, it's elementary. You need zero in order to do modern mathematics. Without a signifier for nothing, there could be no concept of nothing. No concept of nothing. You can't have a concept of nothing without a signifier for nothing. It was introduced, zero was introduced to medieval science with the Hindu numerals, the numerals I was talking about, via the Arabs. Okay, so they didn't have it before then. Without the Hindu numerals, calculations must be performed with Roman numerals. Now, can you imagine that? Can you imagine that? Look at this. You do your multiplication here, right? It's easy. You do 2 times 128, you double it, and then you do 30 times 128 just by simply shifting it over and doing 3 times 128. You add them together and you get your result. Try to do that with the Roman numerals. Now, those Romans, they had this huge empire. They had legions. They had to feed them. They had to get so many loaves per day, so much meat, how many cows, how many days, how far did they have to march? They had to build their aqueducts. They built their roads. They built their colosseums. They had to do multiplication. They had to do division. How did they do it with the Roman numerals? Christian science resisted zero for many centuries, for various reasons. The Indian zero introduced Western science to the number zero. Didn't have the number zero before, the number for nothing, and with the concept of nothing. Zero is necessary to binary counting. 0 and 1, binary counting, we probably know about that, and therefore necessary to electronic computing. All these claims are misleading or false. I would like to say they're all false, but I'll pull back a bit and say they're at least misleading. So, what's going on here? Originally, the Hindu system of numerals was performed on a calculator, on one of these counting boards, okay, with columns. Results were written down in words, so they'd do the calculation with the numerals and then write the results down in words or numerals. Later calculations were written without columns. Eventually results were written with this notation. So you would do your calculations without columns, so you needed a zero, or if you were writing your results down, instead of using, say, Roman numerals we know about, you'd write your results down in these things, then they would use a zero. They would always use a zero. And it wasn't just the Hindus. Lots of other cultures, whenever they needed to use a zero, whenever they needed to signify none or signify an empty place in their counting, they always had a zero. Whenever it was needed, they always had one. So one of the troubles with this history, with the way this history is presented, is that there is a focus on notation. There's this obsession with notation, with what can be written down, what can be signified. And I'll go into that a bit at the end, why perhaps we have this obsession. Because the real story about this history is computers, calculators, reckoners, mechanical computers that were used from China to India to the Arabs to Europe to the Mayans. They had a zero in America before Columbus. they used calculating machines. And so this is what the story is really about. And this is the story I'm going to tell. So this one over here is the earliest surviving one of these calculating machines. Now, we know the Babylonians had them. We know the Egyptians had them. And they probably had them even before they had cities and civilizations, because you could do it in the sand with pebbles. Draw lines and throw pebbles down. Okay? But this is the earliest one from Greece. And does anyone know what the treasurer in the British Parliament's name is? What you call the treasurer in the British... Chancellor of the Exchequer. Do you know what an exchequer was? Exchequer was this huge piece of cloth, right? And all the lords would stand around it, and they'd work out all the taxes and stuff, all watching it, so that they made sure that nothing had gone wrong. So that was a calculating machine. And every shop and every bank, because in the Middle Ages there were banks and shops, and before that, in Greek times and everything, they would have a counter, right? And think of that word counter. When you get all your purchases together, you take them up to the counter. Well, in the old days, in the Middle Ages, right, the counter was a counter, sometimes embedded in the board. Okay, you've got your things, I'm going to add them up, this is how much you owe me. And then, of course, we went to the cogs and wheels thing with in the 17th century with Pascal, and Leibniz made the multiplication wheel and so on. And that's the foundation. I don't know whether my father used to bring home a calculating machine a bit like this, where he'd set it up and wind it. I remember that. And but that's really the basis for those cash registers. Does anyone remember those winding cash registers? From quite a few nodding heads here. They're from quite a long time ago, aren't they now? Yeah, so that was the basis for them. And then, of course, every engineer and every architect would have their slide rule. Okay? And then eventually, 60s, 70s, we got the little handheld calculating machine. But in Japan, in Southeast Asia, people might have seen this, up until the late 20th century, I certainly saw this in Indonesia in the late 20th century, people had these little abacuses. And we'll have a look at them in a minute. They came to Japan quite late, and they came from China, and China had them back in BC times. And in Japan, they were actually so popular that when the handheld computers came in, people were very reluctant to buy the handheld computers, because they said, oh, I can just do this so fast. And these guys are amazingly fast. That's the other thing. I've just shown you how to do the addition and subtract. Oh, sorry, I've just shown you how to count. But they can do multiplication and division really fast on these things. And so I don't need to punch into that. That's too slow. I just do it on my abacus here, on my, it's called a sampan, right? And so what they did, actually, Sharp was very clever. They said, okay, what we'll do is we'll give you a handheld computer, and we'll have embedded in it the abacus as well. And what happened, they made a few models of these, and what happened was people liked doing their adding and subtraction on the abacus, and then whenever they needed to do any big multiplication or division, they would get over and turn the computer on and use that as well. So it's a long history before we came to electronic computing. And this is the main story here, and it's an interesting story. And it all begins with the computer on your hands, right? What was the first computer? Hands, right? And, you know, you just think you can just count, you know, how many sheep have I got? 1, 2, 3, 4, and so on. So hands was probably the reason that in most civilizations, or in a lot of places, you had a 10-based or decimal counting. Okay, you get it in Egypt. You've got it kind of in Babylon. We'll have a look at that in a moment. You got it in China. You got it in Greece as well. This particular system of counting, which Kelsey and I have been practicing, but we'll probably get it wrong. This particular system is quite is quite universal. It's across Eurasia, right? And it's actually kind of got 5 base as well as 10 base, as we shall see. And it is the basis of that Japanese abacus that we were talking about. So let me just show you how it works, right? And you can probably think of this in terms of Roman numerals, because we'll see why. So you start with this hand, right? This hand is the units, okay? And this hand is the tens, all right? And you start counting, you keep your thumb inside there, and you can have a go at this if you like with me. Okay, so keep your thumb in. You've got to keep your thumb in, right? And okay, with my right hand, I'm going to go 1, 2, 3. My fingers are paralysed, but 4. Okay, we get to 4. Okay, are we ready for 5? 1, 2, 3. 5 is the thumb. So think of that as the V, the I's and the V's, right? 5 is the thumb. 6, 7, 8, 9. That's 9, right? 10. These are all 10s, okay? So we can count by 10s now. 10, 20, 30, 40, 40, right? 50, 60, 70, 80, 90. So let's keep going. Let's add a 5, 95, 96, 97, 98, 99. So that's 99. Now, people would learn this. People would learn this up until the 16th century in Europe. Oh, what are you going to use? You're going to use the abacus? Are you going to use this? Oh, no, I use finger counting to do all my multiplication. If it's fairly simple, you can do addition, subtraction, and multiplication using this system. Now, I'm just going to test you guys here. So this is 5, these are 1s, these are 10s, and this is 50, right? So what's 64? Does anyone want to have a go at 64? 64, how are we going? So 50, yeah, it's looking good. 60, and then 4. All right, there we go. So there's that system. Now check this out, check this out. Okay, so match these up with the fingers, okay? There we go there. See, that's the thumb, and there the 4 fingers. This, remember we were talking about the Romans? How the hell did they ever do their multiplication and division? They had this thing. They had big counting boards back at base, but these things were as big as a large mobile phone, 12 centimetres long. They were pocket calculators, right? And they were similar to those ones we saw the Japanese shop assistant using there. Okay, so what you would do is you'd have it in your pocket, you're out there with the legions, you have to do some calculation, you're building the aqueduct, whatever else, and you do your calculations. They do it without looking because they get used to it, and it's like touch typing, and then they would look down at their results and write that down. So this is fractions over here. We're just going to look at a particular part of this, just a very simple part because we're beginners, right? And so you can almost see, but probably not here, that there's an I written in there, in the metal, and there's an X and a C there to tell you what's there. But I've just emphasised it a bit there, and you've got your V's and your L's and your D's. So this is the 5s, 50s and 500s, and you've got your normal I, X's and C's. So you do your calculation, you get your result, and you go, how many C's have I got? Right, put it down. How many L's have I got? Put it down. How many X's? Put it down, excuse me. And V's and 1s. And that's how you do it. You do your calculation over there, not here. You're just writing your results. So people get confused all the time in looking at this history. They're just looking at what's written down. They're not looking at the calculator that was actually used to get to the results. And there's our result there. It's hard for us to read, but after a while, when you know your Roman numerals, you can get used to it. That's 476, I think. Okay, so this is how it seemed to go. You started the counting on your hands. You got a brilliant idea of making it into an abacus, and then you use your Roman numerals associated with the abacus. Okay. So here's an abacus here. This one I think is made out of either marble or ivory or something. It must have been the king's abacus. And over here is the fractions. And they could do amazing things with the fractions. They didn't do decimal fractions like we do, but sometimes they're problematic. They did lots of different combinations of different bases to get a whole variety of fractions. So these counting boards, ubiquitous across civilizations. And we can imagine how they first started, right, with the counting boards, where you would use pebbles in rows. Now, you could just do it in the sand, right? You would just put a pebble there. Okay, 1 sheep, 2 sheep, 3 sheep. Okay, we've got a bunch of 10 over there. We've got 20 over there. We've got 100 over there. And you would just do that. And generally speaking, that's what's done. You'd use unit tokens, pebbles. Do you know what calculus means in Latin?
Pebbles.
Means pebble. Here we've got a Latin speaker here. Calculus means pebble. Okay? And so this is where it came from. But in India, they got an ingenious idea. What they were using what they called dust boards. Okay, and so these dust boards is where you could write something down and rub it out very easily and write something else down. Now, we can think of it, those people who are old enough to remember being in primary school, and you had a little chalkboard. Di was a primary school teacher. Yeah, they have a chalkboard and you'd practice your writing on the little chalkboard. Here's one of them from the 1930s or something there. So we can think of it as a whiteboard or a chalkboard or whatever else. That's what they had. The important thing is you could rub it out, right? So what they started doing was they started saying, okay, 1, 2, 3. They started using numerals in these columns. So the columns had 9 possibilities, and they would start writing numerals down. And you probably can't see this. Now, they didn't have Arial bold font back in those days. So this is the font they used, and this was developing. You know, it was slow to develop the different characters. It doesn't really matter what the shapes were. They changed dramatically, and they changed as it went to the Arabs and the Christians as well, until eventually we got to our various fonts. So that was what they had then, and they would write them in the columns. Now let's just see how this works and compare it to how you were taught to do addition. So what you would do is, if you wanted to add 4 to this number, you would just put the 4 in that column, right? You just write the 4 in. Remember that there would only be single digits in each column, so there's no confusion. And then you say, okay, what's 4 and 3? You've got to know that. And then you get 7. Okay, so we'll now add 5, right? And you put the 5 in the column. So you can pack your column. You can put a whole lot of things in your column, but you need to sort it out. And here we need to sort it out because we need to carry 1. Okay, 5 and 7 equals 12. So we carry the 1, and then we've got to sort out the 1. Now, this is similar to the way you were taught to do it, right? And this is what they invented. Maybe in the, like the 5th and 6th century in India. So you add that up and you've got your result there. So we'll do one more. So we're adding a larger number here, 208. So here we've got 8 and 2 is 10. So we bring that one over. There's nothing in the ones column. An absence signifies an absence, okay? And you add that 4 up and you add that up there. And then you've got this, no problem here that there's no 0 there, there's nothing in this column, okay? There's just, you're just worried about these. And so you say it actually like that. You don't say 300 and no 10s, 340 and no units. You just say 340. And you read it here, 340. No problem at all. So these Hindu numerals were arrived in the Islamic world in the Islamic Golden Age. Now, just a bit of history there. People might remember that the Arab conquest was in the early 7th century, right? And for a while, they were pretty wild. They didn't have a lot of education and everything, but they wanted to get it together by the Abbasid Caliphate. set up a new city, Baghdad, this new city with this huge round, perfectly round wall, double wall to protect it all in the new Baghdad. And in Baghdad, they said, we've got to get civilized here. And they translated Greek and Indian science in Baghdad in what was called the House of Wisdom. And we had a salon about that from a chap called Kamal, Professor Kamal, about the House of Wisdom. Fascinating stuff. What's important for us is there was this dude here, Al-Khwarizmi was here early on, and he was an amazing polymath. He's very important in the history of algebra. And we'll get to algebra a bit later. But what's important for us is the Book of Indian Computation, and he introduced this Indian dust number counting. On the dust board, you do the count, you use these numerals, and this is the way to do it, and I reckon this is the way to go. So he introduced that, but without a zero. There's no mention of zero here. He just introduced the 9 numerals with no zero. 150, maybe 200 years later, there was a change in technique. And we find this in the surviving textbooks. These textbooks tell you how to do it, right? So forget the columns, right? Just do it a bit like you did in primary school in the 60s, whatever. Forget the columns and just write it down, but you need a zero because you haven't got the columns. Okay, so we get this where in the Arab world, they started putting the zero in, so you do your calculation, and then you would go and write it down in words or other numerals, your results. This would all be happening on the chalkboard, not off the chalkboard. You'd use your other numerals there, and we'll get to see what they were. And then there's this other really interesting chap. His name is Gerbert de Aurillac, or we can call him Gerbert, if you like. We'll call him Gerbert. Is that right? What do you prefer? Gerbert. He was a little bit French, but he spent most of his time in Spain, in Catalonia. And I don't know whether people know, Catalonia wasn't just Barcelona. It was this huge kingdom, right? And the Moors were there. The Moors were there in Spain. The Islamicate world was there. And the borders would move. There would be battles and everything. And sometimes Toledo was in the Moorish area, and sometimes Toledo was back in the Christian Spanish area. He was up there in Barcelona. He went down to Cordoba and did some study. He did study elsewhere. When they took over a town sometimes, the Arabs hadn't burned all the books. They would study the books. So there was a lot of communication. There were significant, important people, including Ramon Lull, who we've mentioned in classes, who would travel and could speak and read Arabic and got into this stuff. He found the dust numbers, right? And he made his own invention. Now, I remember reading about this when I was a student, because I was very interested in this. I read about it when I was a student, and it was all very vague. He introduced the abacus, and he introduced the Hindu numerals. And I thought, oh, right, so he introduced both, so you could choose which ones you wanted to do. In fact, it wasn't that way at all. I'm not sure what the scholars thought about that. But this, in 2001, this Charles Burnett, researcher, was looking at a very old religious text, and he was looking on the inside and he's thinking, oh, that looks interesting. And it was a parchment abacus, as it was called, of Gerbert. And this is how it worked. So there's a guy on YouTube who's actually reconstructed this. You should go and have a look at it. He's done a great job. And instead of using dust and writing in dust, maybe he thought, oh, this is a better idea. I'll actually make these numerals into counters. So he actually had cones with the numerals written on them. This guy's got his little hexagons here. And basically it's like the dust numbers, but maybe even better in a way. I'm not sure. Because you think when you're adding, you can just pile in everything. You know, you've got to add a new 200, you've got to add numbers on various things. And you get these piles, and then you start sorting them out, carrying, and work them out. So this is just adding those sets of numbers together. And so he had this system. Now, when Charles Burnett discovered this in 2001, he told a few other people about it, and someone else said, I think I've seen one of those. And so they found another one. And when they turned one of them over, they saw on the back this introduction to the new system, and then this little poem down the bottom. Now, I've just cut the poem off there, and the poem was a mnemonic. Have I pronounced that well? No. It was a way of remembering the names of the numbers. So there's a little poem saying, so you could remember, it's like, learning your ABC with a little song or something. So it was learning the names of numbers. But hey, what have we got down here? So there's the Roman numerals and there's the equivalent. Again, the font's a bit different, right? Right, but that's 1 to 9, and what's down the bottom there? A 0. So this is in probably 900 and maybe 70. We don't know exactly, 960, 970. So before the millennium, quite early, when the Arabs started doing the calculations on the chalkboard without the columns and using the 0, we also see a 0 here. So we don't know if he had a count of a 0 and just put it in that place. It might have got a bit confusing, I think, but here it is. And here's another one where they found it and they got the numbers, and hey, there's your 0 as well. So this is all going on before the turn of the millennium. Okay, so let's now have a bit of a look at the history of 0 and where it might have come from, the Western 0. So a lot of those books I was telling you about make a big fuss about the 0 in India, the numerals and the 0 in India. And we know that it developed, that the Indian system developed in the 6th and 7th century. I'm not going to dispute that. I'm not sure exactly when it began. I think it's a bit vague, but that's okay. And there's this big fuss made about the first 0 in the Indian system. It's actually in Cambodia, on a temple in Cambodia, and there's other later early versions of the 0 there. So the 0 in India back then was a dot. Okay, and so the Hindu numerals developed in India, and the 0 at least by the 7th century. Hindu numerals arrived with the Arabs in the 8th century. Remember we saw that? Arabs used 0 in erasable calculations in the 10th century, and then we got Gerber, of course, doing his thing with these little counters. But where did this Western 0 come from? And this is a big question. Where did the concept come from? So there's a concept of none or place value or whatever else. There's also the number 0, and there's also the actual character, the shape of it. Where did that come from? Was it like a variation on the Indian one? So let's have a look at the arrival of the 0 with the Arabs. So remember, we got the computation without the 0 starting in early on in the House of Wisdom there, and then we get, as I was saying, we get the with a 0 without the columns working on your chalkboard, and we get Gerber here, and we get a whole lot more of 0 stuff happening after that. So we're thinking about this period now before the millennium. Well, actually, where we need to go and look is in astronomy. We need to look at the history of astronomy and see what's going on there, because the most important book of Greek astronomy, the book that everyone, the Arabs and the Christians, wanted to get their hands on, was Ptolemy's Almagest. It was translated before these guys, and it had a 0. So we've got to go to astronomy. How are we going?
0.
All right. 0, nothing. All right. So we go to astronomy. Just a brief outline of astronomy. Astronomy is so important, right? People looking at the stars and measuring the stars had divine implications, everything. People were into astronomy in all these early civilizations. It was the first mathematised science. And it was the most important mathematised science. So the Babylonians, so in this trajectory, Egyptians did astronomy also, but the early Babylonian astronomy is really important to our tradition because they started predicting cyclical events like the things that happened in the solar year, the movement that happened in the solar year, and predicting the wandering stars, the planets, and so on. So they started doing that. But then there was a big development in Plato's Academy. Plato's Academy in Athens, not in Melbourne, way back, where you had Eudoxus, this incredible figure. He's one of my big heroes. We don't have any of his works, but we do know a lot about him, a lot of what he did. And he started building 2D, 3D, you've seen astrolabs or something, started doing those models of astronomy, mathematical, geometric models of astronomy. Now, of course, those guys in those days had the Earth at the centre and everything revolved around the Earth, and they had to explain the retrogrades and so on. But that's where it started. And so it developed. There's a long time between him and Ptolemy, but Ptolemy was in Alexandria, the new rich city on the in Egypt on the delta there that we're going to visit later this year, although it's mostly underwater. Ptolemy was there. He's not the king. People might know that right up until for a long time there were 12 Ptolemies in a row, as in the kings of Alexandria. But this guy also shared that name. And in around 150, they reckon, Ptolemy wrote something called Mathematical Treatise, which then we got through the Arabs, and there's all these bastardizations of the Arab names, and so we call it the Almagest, and that's what it's generally called, is the Almagest. And so this would have mathematical accounts of the solar system. Okay, and that developed and developed and developed, and it's quite amazing, really. It was used for perfectly well for navigation and so on, right up until past Copernicus. You know Copernicus, he had the new theory where the sun was at the centre, right? Right up until Isaac Newton actually worked it all out mathematically in, 1687, and even beyond that. So Ptolemy is really important at this time. People wanted to get their hands on Ptolemy for various reasons, and so the Arabs and the Latins, the Christians, wanted to get onto this, and they did translate it into Arabic early. Now, I want to just to give us a bit of introduction. So we've got the astronomy. We've got the idea of the astronomy being important and astronomy being mathematical. Now we've just got to look a little bit at the numerals that they were using, the Babylonians were using, and then the Greeks, and then the Arabs, and then the English. The Latins. Okay, so it was base 60. What a weird base! Like we've got 9. We got in base 10, we've got nine numerals, right? Imagine having 60 numerals. Why do they have 60 numerals? So many.
Shorthand?
Hello. Well, shorthand, maybe. There's a couple of reasons. The first reason is that 60 has a lot of factors. You can divide 60 by 2 and get a whole number. You can divide 60 by 3, 60 by 4, 60 by 5, 60 by 6, 60 by 7, 9, 10, a lot of factors. And that means they could make lots of fractions, and they could work with it really well, with division, multiplication and everything. So they use that, and we still use it. Right? We count 60 seconds. We get to 59 seconds, and then what do? 1 minute. We count 59 minutes, and then what do? We get to 1 hour. That came from these guys, right? Now, one of the other reasons that it makes sense is because they would also work with 6 times 60, which is 360 degrees. You know, there's 360 degrees in a circle. Why is 360 degrees really interesting? Well, think of the solar cycle. How many days in the solar cycle? It's approximately a year. So if there's something changing cyclically in 1 year, right, you're going to have approximately a degree change per day. But it also has within it base 10. And this is just like your pebbles here. Remember they did in clay marks? They did marks in clay. This is really like your pebbles. There's clay marks there for the units. And then here you've got marks for the tens, right? You're just counting 10, 20, 30. So it has a lot of similarities to what we've been working with. If you think of it like the abacus, these are the units, and they just put a number on each unit, and then they are the tens there as well. Now, so they had that system, and the Greeks, similar system, which is called alphabetical numerals. And what they did, and I'm just using this so that we can see it easily, what they did is they just said, okay, we've got our alphabet here, we're just going to go alpha, beta, gamma, delta, alpha, beta, gamma, delta, epsilon, and so on. We're just going to use these as our numerals, the alphabet. So they just went through the alphabet up to the 9th letter, and then got onto the tens, and then went through the alphabet up to 90, and then got onto the hundreds and kept going. What's this character here? Has anyone seen, any Greeks in the room ever seen that one? It's a very old character. They had 27 letters. Isn't that nice? Because they needed 27 letters to have a letter for every ones, every tens, and every hundreds. So that was their system. That was from before Plato's time. Now, the Hebrews, they copied this system, right? But they didn't have enough numbers, so that was a bit of a problem for them. The Arabs also copied the system. I haven't got this in a nice table. I'm sorry, I'm lifting these tables off the internet, Wikipedia, that sort of thing. But they had the same thing. They just went, let's go straight through, right? And so these are what they were using. So we've got the Greek alphabetical numerals, the Hebrew alphabetical numerals. We've got the Arabic alphabetical numerals. That's abjad just means alphabetical. And we have the Roman numerals. Now, all of these texts were written with these numerals. And whatever language was used, whatever numerals was used, there was always a sign for none, a 0. And this we find in these charts. I won't go into too much to what these charts say, but this is star charts giving longitude and latitude, minutes and seconds. So degrees, minutes and seconds. Remember we were talking about base 60, right? They had a column for degrees, minutes and seconds. So this is a star chart and this is a chord chart tracking a planet, right? And so a planet might go from an occultation where it's 0 and move away from whatever it's being measured against on the horoscope. What's it called? In the stars. Okay. But the important thing is they needed a 0 and they had 1. So this has been translated into our modern language. Okay. And here's an old one here. This is from an edition of the Almagest. So let's just quickly go. The Egyptians didn't have the place value thing, but they had a symbol for none. I got none. Had a symbol, a character. From very early times, the Babylonians needed to use placeholders, and sometimes used them in the text, and sometimes they didn't. Sometimes they just left a gap. But by the 700 BC, they always had a placeholder, and then in the Hellenistic times, in 300 BC, it's a similar time to the Greeks actually, they had a standard 0, and here it is. here's their standard 0. So that's a 2, that's a 30, and that is a 0. There it is over there, just done. So 2 wedges on the side. Now the Greeks had a 0 also in these texts. And you probably can't see it on the screen there, but these are, of course, we always just get copies and copies, so you're always worried about whether they're changing, like the numerals and that sort of thing. But we can see the Greek 0 right back, and scholars believe that it at least goes back to 300 BC, the same time as the Babylonian one. And this is some very old papyrus there, which you may not be able to read what's on there, but this is the symbol that you see there. And this is the symbol in printed text when they started getting printed. So it's like an omicron with a line above it. Sometimes in those old ones, the line's very big, and here the line got smaller as time went on. So from Hellenistic times, both the Greeks and the Babylonians had a 0. And so here's a 0 in one of the copied texts. Here's a 0 from the papyrus. So they varied a bit. And I was actually corresponding with a guy for this talk who put in an application for a Unicode for 0, the Greek 0, and he won it. And so now you can actually type the Greek 0 in your Word document or in your PowerPoint slide. So that's a history of it there. So, where did the Greek 0 symbol come from? Maybe it came from the Indian dot. Don't know. Well, it couldn't have come from the Indian dot because it was way earlier than that. Okay. So, the speculation is that it was the initial of the word Uden, which is their word for none. Okay, so they use the initial. And that's a common thing, right? In the old Greek numeral system, the one that was replaced by the alphabetical one, like say the symbol for 10 was delta, or D if you like, because it's the first initial of deca, which means 10. So this is a common thing. We see it in the Roman numerals as well, with centum and milli, meaning 1,000, and so on. So it makes kind of sense that they did that. They used the first initial letter. And one of my favourite books, my favourite little textbooks on arithmetic from ancient times, this one was made in the 2nd century AD and survived. There's this little place where Nicomachus says, nothing and nothing added together make nothing. What does that mean? We can just write it there. It's a very important thing to say when in the foundations of mathematics, right? So, you know, did the Greeks, a lot of these popular books you read, the Greeks didn't have 0, they didn't know about 0. Well, you know, they knew about nothing, and they knew if you added nothing to nothing, you got nothing. That's in a textbook. Now, why didn't they just use Omicron? If we went back and had a look at those numerals, we'd see when they're doing the alphabetical thing, you get to Omicron, you get to O, little o, right, at 70. So Omicron means 70. So the speculation here is they needed to distinguish the Omicron for 70 from, they need to distinguish the 0, and so they put a line above it. And here we find the zeros in one of these tables that I was talking about earlier. And this one, for me, is really particularly interesting, actually, because what we get here, if I just go back, what we get here is obviously something's moving, and we start at 0 and we count through all the way. Now, there's a big... When I was a student many years ago, I was really into this sort of thing. And I thought Simon Steven was from Bruges, was the first person to do this, to start the counting. Instead of going 1, 2, 3, 4, 5, often they'd put the 0 at the end. He said 0 is the starting place. And I thought he did that. And I got so excited I got my daughter to make a 0 sign in front of his statue in Bruges there. But here it is, probably going back at least to Ptolemy. Okay? Counting from 0. So here are some more we go to the Arabic. So they translated, remember, in the 9th century, and here are those Greek zeros, and we get the Arabic numerals here. So the Greek 0 is being used with those Arabic alphabetical numerals. Okay, and here's more Arabic text with the alphabetical numerals. Okay, so we've got the Greek with the 0. We've got the Arabic using exactly the same 0. And now we go to the Latin. They translated it quite late, okay? But we get a translation from the Arabic, and then this amazing, because a lot of texts were translated from the Arabic. You get the Greek, went to Arabic, and then it went to Latin. So they were often really poor translations. So this one was from Arabic, and this one here was directly from Greek. A bit of a mystery. We know it was done in Sicily. We don't know who it was. So they had these two translations using Greek alphabetical numerals or Roman numerals, and always they used either the Greek 0 or just a simple 0 without the line. And here's one with the 0 without the line, with Roman numerals. Of course, there's no ambiguity with Roman numerals, right? So maybe you don't need to put the line. It kind of makes sense, doesn't it? Whereas with the Greek, there was the ambiguity with 70. Omicron means 70. 70 and 0, big difference. Now, this one is amazing. When I came across this, whoa, this is amazing. This is a Latin text, right? It's a Latin text. It's got the Hindu numerals. Some of you might be able to see them there, just 1, 2, 3. They're actually recognisable. So looking quite modern, right? It's got the Greek 0 for none, okay? And it's also got the numbers are written in the Hindu numerals with a 0. Okay, and you can see that there. You can see perhaps you can see 300, 311, 310. Something's getting closer, right? 310 there with that 0. Again, without the line above it. No ambiguity in the Hindu numerals, right? They didn't need it. Just speculation, but that makes sense, right? Whereas, so we've got a Latin text. We've got the Hindu numerals, we've got the Greek 0, and we've also got the 0 to use with the Hindu numerals. This actual text is just down the road, sitting in the State Library of Victoria. When I was reading the scholarly stuff on this stuff, they're saying, the Melbourne copy, they're talking about this. So I reckon that'll be one of our excursions where we can do it. We all go down there and have a look at this amazing, like it's from maybe 1220. It's quite early, 1220. This was actually copied, like you get copies, of course. This was actually copied in 1220. So it's a wonderful one, and it's so clear and it looks like it's in really good nick, so we should go there. Here's the Greek 0 in Hebrew astronomy, right? And so just showing you a few more here. So this is just where someone's collected all the different zeros that were used in the Latin text. So you can see this one we saw with Gerber in one of them. This is another one here. That looks like phi, doesn't it? But anyway, it was in Latin, so there was no ambiguity there. And this one I really like. So there's an Australian that's into this who I've been chatting with, Andrew Decker. He's in Canberra, and he loves this one. I think he found this one too. So no matter how dark the ages were, no matter how bad the science got in the dark Middle Ages, right? They had to work out Easter. Easter, the movable feast. The first Sunday after the first full moon, after the spring equinox. They had to work it out. So they had to do tables to work it out. And they have an empty space. They have to signify none. So how do you signify none? Oh my God, I won't be able to signify none. It's terrible. They didn't have a problem. Signifying nothing wasn't a problem, wasn't a great problem for the West, the greatest invention that ever happened. They had to signify none, so they wrote none. They just wrote none. Okay, So what I've been talking about so far, a lot of it happened before the millennium, before 1000, and in the first couple of centuries after that. The stories that I remember reading when I was a student about this seem to give a lot of emphasis to the early transmission of the Hindu numerals to the West with Gerber and with other people and the Arabs around that time. But now the emphasis is a lot more on Fibonacci, right? This is like 1202. So remember all those astronomical texts appeared before that. And this is quite interesting. So people might know Fibonacci series. He did it with the breeding of rabbits or whatever else. He didn't do much with it. And so Fibonacci had Arabic sources and wrote this textbook on a book on calculation. It's really interesting, the famous part where he introduces the Hindu numerals. So he says, and you can see it here, the Indian figures up there, and he said these figures there. So he says, with these 9 Indian figures, and then he says, and with the sign, 0, the circle, right, which the Arabs call zephyr, right, which is where we get the term 0 from. So with the 9 Indian numerals and with this, sometimes I see this quoted, right, in these texts, and they just do a ... They leave out this Arab thing, because this is a bit of a hint, isn't it? It's a bit strange, because why wouldn't he say with the Indian numerals, including their 0? Where did the 0 come from? So remember, it had been used as a placeholder no matter what numerals were used. So Fibonacci seems to be saying, yeah, use these, and we're going to now write things down. We're going to write them down, so we need a 0. We'll go and grab the one that the Arabs use in those astronomical texts. So, what's going on? The question that we were talking about earlier, remember 0, dangerous idea, and how it was Platonic and everything, and the West wouldn't do it, and if they had a gap, oh my God, I can't just write none, you know, like it's the devil, right? It's not that at all. Whenever they needed a 0, they used it. But why was... So the question is not so much why was there a slow uptake of 0, because they always had one when they needed it. The question is not even why the slow uptake of the Hindu numerals. The question actually is, why did it take so long to move to recording Hindu numeral calculations on paper? Why did it take so long to do Hindu numeral calculations on paper? Okay, so here's the image that I used to promote this, and we've got 2 chaps here. One's using the Hindu numerals to on a erasable board, and the other one's using his abacus, his counting board. So let's just have a look at the history here. Just remember. So we had the erasable numerals in the columns, which were in India, right, and came to Arabia, and then the Arabs said, okay, let's use our chalkboard like we did in primary school, but we're going to use the 0 and put it in the columns. And this continued for a long time. And this image here, which is from 04, if I've got that right, this is about which is best, the abacus, right, or the algorist. So there were these people who were skilled, and they were called algorists because they knew how to use the numerals, and there were people who knew how to use the counting board, and they were called the abacists. So which was better? So this was going on right into the 1500s, even into the 1600s, and lots of people were still learning the finger thing. So people who had to do fairly simple calculations would go to school and learn the finger thing, and they were perfectly happy with that. If you needed to do something more advanced, you could use these systems. It wasn't until the 1500s, and this was scientists, right, and more generally later, that you actually started writing down the Hindu numerals on the page. And when you started doing your calculation on the page, And when you started writing your results on the page, why bother translating it into Roman numerals? Why not just use these numerals? And that's what happened. After a while, because they're doing everything on the page, they just used the Hindu numerals. But that happened slowly. And just have a bit of a look at that. We've got actually Galileo and Kepler, famous in the history of science. Kepler especially important in the history of astronomy, very important in terms of what Newton did much later. And here they are starting to do calculations. You can see the columns running across there, and these have survived. So this is getting quite new. And another thing that's really interesting is because, of course, when you start doing the calculations on the page, then you can start using other mathematical notation. Okay? But when did this happen? Here we've got the plus, right? We've got the plus there, 1360. We've got the minus came in what, 1500. We've got equals coming in, 1560, and then there's this explosion here. This is just a Wikipedia page. You can link through on all these and work out them all. But it gives you a nice pattern there, doesn't it? You know, plus, minus, and then this explosion, which happened about 1600. Why did the explosion happen then? And this is the same time that people started writing down on the page. Because look, what we are talking about, here's Fibonacci, he was quite late. What we're talking about Gerber and before that with the Arabs, is way over there, a long way away from what was happening here. There's this big gap. So this big gap does need to be explained, but it wasn't about the devil in the zero. It wasn't about Western resistance to the zero. It was just about more profane things. I want to show you one more thing here, which is really fascinating. So in the early 1500s, they were doing their algebra and they were trying to get general solutions to cubic equations, right? And you don't need to know what that is, but it's very complicated and very difficult. And what Tartaglia did was amazing and still considered really important in the history of algebra. When he worked it out, when he finally sent it to Cardano, this is what he sent. So this is the modern notation of it. This is what he sent in words. He wrote the algebra out in words. We think of algebra as all these characters, right? This is what he sent to Cardano to give him the solution to the algebra. It wasn't until 100 years later with Descartes that we even got like x squared, x cubed, that sort of symbolism. It all came really late. Why did this all come really late? And here it is, you know, like we got so many more symbols after that. Why did it come really late? Paper. The availability of paper. Gerber didn't have paper. There was no paper in Europe at that time, right? They used parchment. His board, he used what he had. He used parchment, he drew up his thing, and off we go. The Indians used the dust boards and so on. There wasn't any paper. Paper came from China, was invented in China, it went through the Arabs and eventually arrived in Europe. And you can see here, paper mills started opening in Europe in the 1300s, in the 1400s, and then there was the invention of the printing press. Okay, now it's interesting to think about the inventing of the printing press, because definitely when the invention of movable type with Gutenberg, right, came in, then obviously, and it was popular, there would be demand for paper. But we can think about this the other way around. If there, just in extreme case, if there's no paper, there's no need for a printing press because there's nothing to print it on. It was only when paper mills started being established in Europe and paper started to be used that there was a need, a demand to do printing rather than to just do the copies. So there's not much to see here. Printing mills here. Price of books. This is actually price of books. It's hard to get the price of paper, but then there's a collapse in the price soon after, not directly after, but soon after the printing press. Now, paper was still very expensive. You see, if you've ever read a biography of Kepler or of, he had a big problem getting the paper in order to publish his Rudolphine tables. He had to get a fortune together in order to publish them because he needed to buy the paper. And if Isaac Newton, he used to write really small. He used to write in the back and the side and everything because paper was expensive, but nowhere near as expensive as it used to be. And so you could do your notebooks. You could write, because the mathematicians started writing to each other, writing letters to each other, writing their calculations. See, look what I've done, check it out, and so on. They were writing their calculations on paper. They were writing the results on paper. Why not just keep using the Arabic numerals and get rid of the Roman numerals? We don't need them anymore. So this is a picture of Nuremberg, very proud Nuremberg. It's in this was made in 1493. They had their first mill in Nuremberg in 1390, and it's prominent down here, the paper mill. The paper mill was a proud thing. Like you might say, you'd be proud of having an airport in the 50s or something, or a data centre in your city, when we're all going data or whatever. They had the printing press. We've got a printing press. We can do that stuff. We've got a paper mill. We can do the printing. They did a lot of printing in Nuremberg as well. It's a very important centre for that. So paper was important. Paper came in so late, and that, it seems to me, is the reason why the move to calculating on paper was so late, and that is why the move to the Hindu numerals with the 0 on paper came so late, because you could do perfectly well with what you wanted to do with the mechanical machine or doing your calculations on a chalkboard. So, how are we going? So, remember all these books? Remember what they were saying? The greatest invention of all time? This is a 0. It introduced the concept of nothing, all this sort of stuff. This guy's going to India to find where the 0 came from. That really set off Western science, because once you had 0, once you did all this calculation, you could do Einstein and so on. Okay, so let's look at their claims then. 0 is elementary to modern mathematical science. No, it's not. Because an absence can be signified by an absence. On all your counting boards, it can be signified by an absence. It's only a necessary thing you have to do when you're doing your calculations on paper. Without a signifier for nothing, there could be no concept of nothing. Well, that is the weirdest one. When I read that, I just can't believe it. An absence can signify an absence. You don't need a signifier for nothing. You can just have a gap. Right? How many fish did I catch? None. Right? How many fish did I catch? 10. How many fish did I catch? None. Isn't that the concept of nothing? Introduced to medieval science with the Hindu numerals via the Arabs. Well, they had it way before. The Babylonians had it, and then in the Greek astronomy, they had the symbol for nothing, the circle with a line over it. So maybe there was some influence, but it certainly came a lot later. With the Hindu numerals, calculations must be performed... without the Hindu numerals, calculations must be performed with the Roman numerals. I don't know how many times I've heard people say this. And it's so absurd, because you think that must be wrong. The Romans couldn't have run the Roman Empire when they had to do their calculations using Roman numerals. They would have invented something else. And it's ridiculous, because we know that they had this wonderful pocket calculator as well as other calculators back at home. So Christian Science resisted 0 for many centuries. I haven't gone into these claims. They're just ridiculous claims. The 0 was used when they needed it. When they needed to put in the Easter calendar, they used none. Right? That's a symbol for 0, but maybe if you want to say it needs to be abbreviated, they had the Greek one as well. The Indian 0 introduced Western science to the number 0, and with it the concept of 0. Well, I kind of think they had it long before. The zero is necessary to binary counting and so to electronic computing. Okay, so... to electronic computing. Now, let me just show you a bit. Oh, sorry. Okay, so let me just show you about electronic computing. You know, they say binary numbers, 0 and 1, right? 0 and 1, you need that in binary. You don't really need to know how to do binary counting, but it's 0 and 1 in binary counting, isn't it? And the computers, they need zero. It's all zeros and ones running around, you know, and it's all based on zeros and ones. Well, is it? Is it based on zeros and ones? Or is it just based on ones? Right? It's a gate, right? You've got a current running through. Elementary, at the very foundations, the physical foundations of your computer, you've got a current running through, or you break the current. Current, no current. Current, no current. So you've got one, and then you've got the absence of one. So you think about it in terms of beads, you've got one, and you've got the absence of one. One and the absence of one. You've got a current and the absence of a current. It's not 1 and 0, it's 1 and an absence. Now, I need to remember this because it's kind of confusing. It's kind of confusing talking about nothing and signifying nothing. So I need to have my notes just to finish off. So with electronic computing, right, an absence signifies an absence. Nothing signifies nothing. It's only when using notation that you need the inconvenience of signifying nothing with something. But in all these books, right, the zero is more than an inconvenience. It's like the greatest thing ever invented. So why this obsession with signifying nothing? Well, part of the story here is like there is a bit of a dramatic story, isn't there? We've got this invention in the Orient, right, coming across to the Christian West, conservative, medieval Europe. Oh, no, it's the devil, it's Satan. No, we can't have that. So, and then they finally accept it after 5 centuries or 2 millennium, as someone says. They accept it, and then science takes off, and we get this amazing science. So it's a great story, isn't it? And also that it's nothing that's being given, you know. It's kind of like, whoa, nothing is being given, or the symbol for nothing. So perhaps it's a good story, but I also think there's something else going on here, because I've had this with me all through my life, and I really wanted to give a talk about it. And as a Platonist, it's really annoying and confronting. So it's something about the Western mindset and about modern philosophy where knowledge and the communication of knowledge are considered to be the same thing. What we know and the communication of what we know seems to be the same thing. It's the reduction of knowledge, of wisdom, whatever, to linguistically communicated or semiotically communicated with signs. All that we can know can be said or signified. This is a powerful philosophical view, and it's anti-mysticism and it's anti-Platonic. And it's anti-Platonic because for Plato, words and signs give an account of what you know. They're not what you know, they're just the way you give an account for what you know. And there's a lot that you know that can't be said. But for those who want to reduce what we know to what can be said, it's like nothing is the last frontier. Think no thing, right? Think none is a shortening, not one. We're trying to say nothing, right? We're trying to say nothing, refer to the void, the absence. But it's an absence of a presence, right? It's not a thing, no thing. It's and so when you're referring to something that is not, that doesn't exist, not it, You have to say not being it. So non-being or non-existence, you have to refer to existence. You have to refer to something that is. You can't refer to nothing in itself because it is always not something else. You can't refer to nothing in itself because it's always not something else. Non-being is not being. Non-existence is not existence. You have to refer back to something exists. If you do try to refer to nothing as something in itself, then you are thinking of it as something. If you refer to nothing in itself, you think you can refer to nothing in itself, you're thinking of it of something. You're introducing a confusion. And this might not sound like very much, but it has profound philosophical implications, as some of our students in the academy know, because it was very important to Plato. It was very important to Plato because Parmenides, he came up, Parmenides in the 5th century pointed out the problem, and then Plato in his dialogue, the Sophist, solves the problem. Okay? So we're not going to go into the deep philosophical issue, but we are going to say that to deny that there is this, that nothing can't be spoken about, is to deny Platonic philosophy, is to deny mysticism. So absence cannot be referred to in itself, and so this brings us to zero, the signifier of nothing. See, zero is supposed to signify nothing. In the celebration of the signifier of nothing, as though it is something to be celebrated, we are obscuring the truth about nothingness. We are expressing a common modern and profound confusion. In truth, nothingness in itself cannot be said. The best way to refer to absence is with an absence, like we did on all our counting systems. There's no tens, right? The celebration of the signifier of nothing is a celebration of a prevailing modern confusion. So that's it.